maybe more science journalists. Okay, so extreme weather, is it here to stay? So I think maybe this week we had a kind of an example of extreme weather going from a record cold to actually a pretty nice day today. And we're always worried about weather, especially a day like today when we're having the Grey Cup, you know, outdoors in a place where I used to live, Edmonton, Alberta. I'm happy to report it's +1. So I think everything will be fine. Everybody remembers the fog bowl here when the fog came in from the lake and they actually had to delay the game. So Earth is a complex system, and water and land and atmosphere are in constant dance, illuminated and heated by sunlight and nudged by these massive geothermal forces. And we even have impacts from space, of course, the sun being primary of those. And increasingly, human activity. And modeling such a system of this complexity is certainly a challenge. We have an expert at this. But it's essential if we really want to understand what humanity faces in the era of changing climate. So today we're pleased to welcome one of Canada's foremost climate scientists, Professor Richard Peltier, or Richard, Dick Peltier, if we want to say, who will show us how physics and computational methods, so using the power of computers, are used to create models of our past and future climates. So Dick's a geophysicist. His investigations of thermal convection and geothermal hydrodynamics led him to an interest in computational modeling. And his work includes studying nonlinear processes in the atmosphere, including investigating the connection between ice ages. Who was here at the last ice age? We're under a few, no one, okay. We were covered with ice at one time, as you know, right? It has receded, actually fairly recently in time, to variations in the Earth's orbital geometry. In all of these demanding subjects, he brings a penetrating mathematical skills, not my strength, I'm afraid. Are you going to be showing equations?
Certainly not.
Okay, very good, okay. That's great. I love you already. That have set a new standards in analysis. So Professor Peltier has been extremely productive teacher, advising many students who have become outstanding scientists in their own right. I was just in Leeds yesterday in UK, and he has a postdoctoral fellow who's there now, working there. And he's elected a fellow of the Royal Society of Canada, the American Meteorological Society, and the American Geophysical Union, that of which is an honor bestowed only on a limited number each year, so it's quite an honor. And often only after a lifetime of internationally recognized scientific leadership, which certainly describes Dick. So if you want to come to the stage, we're keen to hear your presentation on extreme weather. Is it here to stay? Please welcome.
It's a great challenge to try to hook yourself up.
You can use a supercomputer. So.
Maybe I'll just answer the question straight away. Yes, it's here to stay. Okay. Can you hear me? Great. So I've been asked to speak to this very suggestive topic, and I'm going to do my very best to take you through what science has learned over the past 10 years or so on not only what the answer to this question is, but how it's actually been obtained. So I'll start with a couple of examples of severe weather events which you probably are all aware of. They spent a great deal of time in the news over the summer. Looking on the left, this picture is of the famous BC wildfires that occurred just north of Burns Lake in northern British Columbia, where I happen to have family living. And so I was on the phone every second day with my cousin saying, "Are you okay? Are you okay?" So this was a very, very serious problem in northern British Columbia. In France, about 2 months ago, you may have also been conscious of this huge precipitation event that hit the south of France near the Pyrenees Mountains. It was astonishing. It basically floated cars and everything that was in its path. Another example, if you like, of the kind of extreme weather events that we're having to increasingly cope with as the system evolves. This is an example of a comparison, again, for 2018. Both of these previous examples were 2018 examples. This is basically comparing heat waves as observed during June of 1976 on the left, right, and June of 2018 on the right. And you may remember the problems in South Africa earlier this summer, which were not only very severe heat wave, but which led in South Africa to the almost elimination of the water supply. So these events have been extremely severe, and they are becoming, as demonstrated on the right, more frequent. So what can we say about them going forward? This is the issue. Let me talk a little bit at first about the background of climate change within which these extreme events are occurring, right? Just by way of introduction to how we can actually predict what we will have to face in the future if we do nothing about the problem of greenhouse gas-induced global warming. So here is basically the latest mean surface temperature analysis. That's the background within which extreme events are occurring. If you look on the left-hand side, you will see that we are up by around approaching 1 full degree centigrade above what we call the pre-industrial level. That was the level that existed of carbon dioxide concentration around 1850 to 1870, before we actually started to burn fossil fuels. On the right-hand side, this is a picture, a blow-up of the segment of that record on the left from 1950 up to 2018. And you can see in this record, and I'll show you a little more data on this momentarily, here is the super El Nino that took us up to a change in mean surface temperature above 1 degree centigrade, and briefly, of course, just during the El Nino period. But you'll know that in the Paris Agreement, we have a commitment, an aspiration, rather than a commitment, an aspiration to keep the rise of mean surface temperature below 1.5 degrees centigrade. Okay? So during this last El Nino event, we got pretty close to hitting it already. Here's a picture again of the latest data from Mauna Loa, from Keeling's site, original site on the island of Mauna Loa in Hawaii, basically going from 2014 up to now. And you can see there is the same increase, continuing increase of carbon dioxide concentration in this region that has, of course, been occurring continuously over the past time since Northern Hemisphere industrialization began. I want to just draw your attention for a moment to the comments at the bottom of this. I think it's really very important for me to tell you exactly what I think of the state of the science in terms of the global picture as it's evolving. I'll say that it's an unassailable truth that atmospheric CO2 concentration is caused by human-induced fossil fuel burning, and that the CO2 increase is the unambiguous cause of the continuing rise of mean surface temperature over the past 50 years. Okay? There is no alternative to this truth. Okay? So science speaks to the issue of truth, and truth is determined by the quality of the argument that takes us there. Just to remind you again as to what's been happening from a spatially disaggregated perspective on the global warming issue. So here's warming of the surface of the Earth by decade, right? Starts off benign in the 70s, and these are averages at every grid point on the surface of the Earth of the mean surface temperature in that grid point, okay? So this is the next decade average in the 80s, 90s, 2000s. And you can see what's kicking in the system is this intense northern hemisphere polar amplification, right? And this is very well understood. There's nothing complicated about this. It's a consequence, really, of albedo feedback. As the system warms over the northern hemisphere Arctic Ocean, sea ice in the ocean is melting back. The fraction of the land which is covered by snow in the winter is decreasing, right? Both of these effects enable the Earth to absorb more incoming energy from the from the short wavelength emission from the sun, and there is therefore a strong positive feedback. More absorption of energy, more melting, more warming. Okay? Let's look at the 2018 record. Okay? So here is, on the left-hand side, if I can see this properly, we're looking at October 2018, and then the average from August to October 2018 on the right, and then in the left, an annual average where we can see this 1 year average from 2017 to 2018, which again shows this northern hemisphere enhancement of warming. I'm really showing you this picture because I want you to notice this figure in the bottom right, okay? So here is the famous 2015-2016 El Nino, which occurred really at the time of the Paris conference, right? And you can see that at that time, again, at peak, the mean surface temperature had risen almost to 1.4 degrees centigrade, okay? Almost hitting the 1.5 degrees average temperature increase, which Paris thought we should allow ourselves, at most. So what I want to do now is to talk to you about the future and about how we infer it, okay? Only models can actually enable us to reach into the future. And of course, when you talk in terms of models, you always have to address the question as to whether they're reliable, how biased they are or unbiased they are, right? So there is an art in the big data science that's required to enable us to look forward into the future with as clear a view as possible. So here's an example of the models which we use to do forward projections. This is a global model. It's the one that is exercised most commonly in my own group. And what I'm showing you here is an image, right, at every pixel in the model of the vertically integrated water vapor in the atmosphere. And the closed white circles are really the regions in which rain is occurring. Okay? So most of this talk, in terms of talking about severe extreme events, I'm going to be focused on rainfall, right? So I want you to understand that the global models that we use to make predictions, right, are global models which capture all of the fundamental physics in the climate system. These models consist of coupled oceans, three-dimensional oceans and their circulation, three-dimensional atmospheres and their circulation, sea ice cover, and small-scale processes which have to be parameterized like rain. Okay? So these are the models which allow us on global scale to look forward into the future. But we're going to be talking here about extreme events, and all extreme events, I'll make the comment right away, are local, right? And so we have to have a mechanism to enable us to translate the global pictures that are generated by models like this into local understanding, right? So that's really the goal in this talk. But first, let me show you some ideas of the natural variability in the system above which an event has to rise before we can call it extreme, right? If the event is just buried in the noise of natural variability, there's nothing really extreme about it. It's just one of the more moderately strong events of that kind. And here what I'm showing you is a data set from Clara Desser at the Boulder Laboratory, basically showing a 40-member ensemble of global calculations right through the time from the beginning of Northern Hemisphere industrialization up to the present, okay? This picture is in terms of its regional variability, but showing you the regional variability in temperature, okay? So on the left-hand side, in this regional variability, I'm showing you the average in the top left. The middle of the left is the hottest variability, contribution of the variability, and on the bottom, basically, is the coldest contribution to the variability over the North American continent, okay? And on the right-hand side of this figure, I'm showing you the range, right? The spread, right? From cold to warm. And you can see, looking at the figure at the bottom, well, let's start at the top, at particular locations of cities. When you come down to a really small scale, the variability is huge, right? So you need to average over a sufficiently large area, for example, the continent, before you get really tight constraint on the mean surface temperature and its evolution. And here, when we average over the continent, you can see that we fit very nicely the actual observations, right? This is from a 40-member ensemble integrated at roughly 100 kilometers horizontal resolution, right from the beginning of Northern Hemisphere industrialization up to the present. And I can show you the same thing in terms of precipitation. And here the fluctuations are even wilder, okay? So precipitation is a really hard field for a model to hit, okay? And this is why I'm going to focus on it for the purpose of the discussion this afternoon. So again, range is shown on the right, and wettest and driest and average are shown from top to bottom, okay? So when we talk about extreme events, we have to be talking about events which rise above this natural statistical background, okay? If they don't rise above this background, then we have no basis on which to call them extreme. Extreme relative to what? Okay. So I'm going to focus on precipitation extremes for the reason that this field is really the hardest to get. It turns out to be very simple to make accurate predictions of the variation of mean surface temperature so long as you're averaging over a reasonable region, right? Precipitation is much more challenging. And what I'm going to do here is talk about three regions, right? I'm going to talk about the Laurentian Great Lakes Basin, where we live. I'm going to talk about Western Canada, where most of my family comes from. And I'm going to talk about the really challenging, most challenging region for precipitation is really the India and the summer monsoon region. I'm going to apply the same methods to each region, and to cut to the chase, I'm going to tell you right away, and I'll explain this at the end, that basically the expectation in terms of the increase in the extremity and periodicity of extremes, right, will turn out to be about the same in each of these regions, okay? Right? That's basically the bottom line, what I have to say, and at the very end I'll explain to you why this is so, okay? Okay, so we're after understanding weather and climate extremes, and I'm going to employ a methodology which is called dynamical downscaling. Dynamical downscaling, right, rather than statistical downscaling. I'm going to employ a method which takes the results of the global climate model, right, and using a particular methodology, which I'll describe to you, how do we get down into a region as small as the Laurentian Great Lakes Basin of Ontario and the northern US. Okay? So we want to go from this global picture, which is characterized by strong northern hemisphere polar amplification, right, to this picture, right, where extreme events are occurring at the people scale. So the way we're going to do this is using this method of dynamical downscaling. And what I'm showing you here on the sphere is a picture of the average skin temperature of the Earth under modern climate conditions, right? And the way I'm going to do this analysis is I'm going to embed within this global picture, right, multiple domains of increasingly higher resolution. The first will be at continent scale, right? The second will be for eastern Canada over Ontario and the Great Lakes Basin, and then over western Canada. This outermost domain, I'm going to run at 30 kilometers horizontal resolution, whereas the global model is running around 100 kilometers global resolution, right? And in the inner domain, either one or the other of these two inner domains, I'm going to run at 10 kilometers. And I'm going to explain to you why this is necessary in order to develop information that's actually policy relevant. Let me put it that way. So this is an example, a sketch basically of the pipeline, the way this works. And I promised I will not show an equation. You're going to be a good person, okay? Right? So the way this works is we take data, right, from the global model, we process the output of that data, right, and then apply it at the boundary, right, first at the outermost boundary. We absorb that data from the global model along the perimeter of the first outermost domain, which is going to run at 30 kilometers resolution, and then we're going to take the data from that model, which is running at 30 kilometers resolution, and we're going to ingest it in the innermost model, which is running at 10 kilometers resolution. So this is dynamical downscaling, right? We're not doing it statistically, we're doing it with full dynamical control. So let me show you pictures of what the global temperature field looks like, for example, coming from the global model, right, with North America in the middle, right? So now we're going to come down at the same instant of time to 30 kilometers resolution, right, in the first of these innermost domains, right? And you can see we're starting to pick up a little more structure. But you'll notice even here, you hardly see the lakes. The lakes are basically non-existent. Okay? This is a problem in Ontario and the Great Lakes Basin. We've got a lot of lakes, okay? And they cover a huge area of the surface. And they contain water, right? So there's a source of water vapor, right? And this has a huge impact on climate. And the only way we're able to get accurate projections of what the evolution of climate should be in Ontario and the Great Lakes Basin is to properly deal with the lakes. And you can see the way this works. We come down one step even further. Now we're at 10 kilometers resolution, and the lakes just pop out at you, right? They're the dominant feature, basically, in the domain. So to show you in an animation what's going on, right, in the dynamical downscaled results from the innermost domain, where the winds over the region are shown as arrow sticks, okay, and temperatures are shown in color. So we're actually fully resolving the meteorology in this highest resolution innermost domain, right? And so as storms pass over the region, the lakes in this particular range of time are anomalously warm, but then when particular events occur, the lakes cool down. And in this model, we have fully coupled representation of the lakes for the first time, done here at the University of Toronto. So this is the game we play now. So we now have very high resolution in this innermost domain. This is the big data problem, which is coming from, typically we'll run under modern conditions for 15 years, and then to go to mid-century, we'll run for 15 years, and then to end century, we'll run for another 15 years. And we'll take all of the data, right, from these runs and compare them to one another statistically. So this is the downscaling pipeline that is employed to do extreme events analysis, right? So here's the global model. We first come down to 30 kilometers. We then come down to 10 kilometers, and it's these data which we actually use to address the question of extreme events. Just to show you basically what these results suggest, not in terms of extremes, but in terms of mean climate over Ontario and the Great Lakes Basin going forward, right, are under just to mid-century. So this is another about 30 to 40 years away from today. And notice here first on the temperature field, and we're showing basically monthly data of Tmin, Tmax, and Tmean, right, for every month through, as an average over 15 years for all of the data. And you can see the average increment of surface temperature over Ontario and the Great Lakes Basin by mid-century is already between 3.5 and 4 degrees, okay? Now, you should understand that the IPCC predicts, using global models, that the increase in mean surface temperature at the end of the century is between 2.5 and 3.5 degrees, okay? So you need to ask the question, right? My goodness, how could it possibly be, right, that in this local region we're almost the same or somewhat higher than the warming that's expected to exist at the end of the century? Well, as in most of these climate-related issues, the answer is actually really very simple. It's like the answer to the question of why northern hemisphere polar amplification. Here the explanation is just simple. We live on a continent. We do not live in the oceans. The heat capacity of land is far lower than the heat capacity of oceans. And so a given amount of energy input will cause a larger increase of temperature, okay? So this is readily understandable, but most people don't understand that just because we live on a continent, our expectation of the degree of warming is much, much higher, right, than we would expect on the basis of the assumption that it should be the same as the globally averaged amount of warming, okay? And here for precipitation at mid-century, you'll see that the greatest enhancement of precipitation expected in this region is in the shoulder seasons, right? In spring and fall, okay? So now we want to get into the business of extremes. So this is extreme events analysis. How do we do it, right? So we've got a huge data set that comes from the highest resolution innermost domain, and we want to analyze it for extremes and for extremes going forward in time. How do we do this? Well, first order of business is to produce a method that we can use to control, right, the biases in the model, right? And I've already shown you Clara Desser's results, global results. We need to do the same thing here. So I'm going to show you results from what I call a mini ensemble of different high-resolution models, which are embedded within the global model, right, which differ in their design by varying the nature of the schemes, the methods which are used to represent unresolved physical processes, like small-scale precipitation-related processes, like turbulent boundary layer processes, like the way in which we describe the way incoming radiation from the sun interacts with the cloud field, okay? This is called a physics ensemble. We know that there are many ways that we could describe the unresolved processes in the model, and because no one of these sets of processes is perfect, right, what we do is to try to control for bias, right, by building an ensemble, which means we need to integrate many, many times in order to stabilize the result against the biases in individual models. And this is basically what I'm showing you here is the average over the model ensemble in terms of precipitation, and then the biases of the 5 individual members that make up the ensemble. And you can see there are different biases in each of the members. We can do the same thing here for temperature. And you can see over this region a very interesting characteristic of Ontario and the Great Lakes Basin is that there's a very strong gradient across the lakes themselves, right, between warming and cooling, right? This is a region of very, very strong gradient in both the temperature field and the precipitation field, which makes this region especially challenging to analyze. So how do we do this? So I'm going to show you a couple of different methods on how we do this analysis. But let me walk you through the simplest method, which I'll start off by discussing in the top. This is called a peak over threshold method, right? So we first, and I'm showing you here data from Pearson International Airport, right? Just to be very, very specific, okay? Let's say we define an extreme event as involving the top, let's say, 2.7% of all events measured in the severity of precipitation in millimeters per day, right? So we take those 2.7% of data, and we build a histogram, right, of the data. And in this case, we've got 70 or 80 years of data, and we get a nice clean histogram. We could now take data from the model, again, under modern conditions, but focusing now just on a smaller range of time. Actually, we're trying to mimic the same range of time as in the Pearson data, and we can build a histogram based upon that data. And what we can now do is to plot the return value, right? How often an event of a given severity occurs as a function of the return time, right? And what I'm showing you here by comparing black and blue, the bruise, if you like, okay, is that the two data sets, when bias corrected, lie right on top of one another. Now, I need to explain to you what the bias is derivative of. Even though we're running the innermost domain at relatively high resolution of 10 kilometers, you understand that our estimate of precipitation in every point on the grid of the model is an average over 100 kilometers, right? Whereas individual precipitation events occur much, much more local. So that's an origin of bias in our ability to fit the tail of the probability distribution, right, using model output. Even though we're running at such reasonably high resolution, there's still a bias we need to correct for, but it's correctable very, very simply. And it leads to basically blue and black overlapping, right? And if you look at what this means, then the 50-year event, which has an intensity, repeat time of 50 years, in the data, has an intensity of about 100 millimeters per day. From the bias-corrected results, right, that 50-year event has an intensity of 102 millimeters per day, right? So we've done a very good job, right, of bias correction. Now we use the same bias correction going forward using data from mid-century, okay? So we take this data from mid-century, right? We, again, use the top 2.7%. We bias correct in exactly the same way to get the tail of the probability distribution. And we discover, through analysis, that a 50-year event, right, going forward, right, has an intensity of 151 millimeters per day, right? Whereas a 20-year event, right, has an intensity equal to the original intensity, all right? So we've collapsed the time between precipitation intensity events of 100 millimeters per day by a factor of 2.5, okay? Right? Just by mid-century. So this is a huge increase over this region of the intensity of extreme precipitation events, right? But I need to make the following point very clearly, okay? And I'm showing you here a picture of the famous Toronto flood of 2013. I was actually driving on Jarvis Street towards Bloor at the time this event occurred. I had to stop the car. I could see nothing, right? It was a total deluge, right? So there is a problem in all of this, and you need to understand what I'm not claiming, right? So the issue of attribution of cause, okay, is a very serious problem, right? In order for us to say that this particular highly local precipitation event was caused by human-induced global warming is a step that we cannot yet take, although there's a huge amount of work going on in the community, mostly focused on on hurricanes, right? Which is leading some of my colleagues to believe that they can make a clear attribution. But the amount of effort that's going on in this area is such that I expect that over the next 5-10 years, we're going to be in a much stronger position to unambiguously attribute specific extreme events to human cause. So just a little more data now, basically disaggregated in space, right, from these analyses for Ontario and the Great Lakes Basin. Here's a comparison, future precipitation changes, annual averages. Here is the 1979 to 1994 observed data set, okay? And here is the simulated 1979 to 1994 data set. These are future precipitation changes, not extremes. But you can see how beautiful the 10-kilometer resolution model is capturing the basic structure. This gradient from the bottom left to the top right, okay? All of this structure is picked up in the simulated result. Going forward to 2045 to 2060, what we're calling mid-century, you can see here by eye the increase in precipitation intensity. And just to drive the main point home from this initial analysis of Ontario and the Great Lakes Basin, here are the station locations shown on the left. Here simulated 1979 to 1994, and here simulated 2045 to 2060 extremes, okay? Right? And so the increase in the extremities from the increase in the mean is very clear. The extremes are more strongly affected, right, than is the mean. So again, precipitation amplitudes of 50-year events increase by 14 to 29% by mid-century, right? Current 50-year events will occur more frequently every 25 to 15 years. So you understand, this is a huge effect. So let me move forward to talk very quickly about Western Canada. So whereas, I'm saying in this slide, in Eastern Canada and the Great Lakes Basin, the regional issue is the lakes, okay? In Western Canada, clearly the regional issue is the mountains, okay? And when we do this downscaling analysis, we wouldn't do it unless there was something characteristic of the region in which we would expect higher spatial resolution to give us more accurate results. So clearly the lakes are one of these issues. But the mountains in Western Canada are another issue, because you'll understand that the Rocky Mountains continental divide a moist climate regime to the west in British Columbia from a relatively, in fact, often very dry climate regime to the east over Alberta, okay? So this is very challenging because of this enormous contrast between the climate regimes of these two regions. And you can see immediately why it may be tough to do an accurate analysis of this. Sort of here is the global model's depiction of topography, okay, over that domain, right? And here is the 10-kilometer resolution topography, okay? So as the resolution goes up, and it's not clear actually that 10 kilometers is enough, okay? But as the resolution goes up, the mountains, the peak topography in the mountains rises, right? The quasi-plateau that separates the peaks of the Rocky Mountains from the coast mountains becomes more well-established. The rain shadow regions become more well-established, right? So what we want to do now is to play the same game that we have played in Ontario for Western Canada. What are the impacts of the global warming process going to be in Western Canada on precipitation and precipitation intensity? So here are the two domains again. So in Eastern Canada, I used exactly the same outer domain on continental scale, but now I've shifted the innermost domain over Western Canada. And this is a beautiful aspect, if you like, of the way the pipeline we've developed works for this kind of analysis. We can shift that inner domain wherever we want to put it. So here's precipitation climatology over Western Canada. Here is basically observed precipitation climatology from merged data sets. Right? Here is the prediction of the precipitation climatology over the region from the global model. Okay? You can see that it's hopeless. Right? The huge rain rates that occur over the coast mountains, which I was so unhappy to endure every year of my young life that I spent as much time as possible in Mexico. So this global model really misses that entire structure. So as we come up, eventually, first at 30 kilometers and then to 10 kilometers, you can see we're capturing, even at 30 kilometers, we're still not isolating the islands off the west coast of British Columbia, right? Never mind topography, islands come joined together, et cetera, et cetera. So here we start to isolate at least Vancouver Island and some of the other larger islands off the U.S. west coast, the BC west coast. So resolution is a huge issue. But first, to show you basically results for warming. And I'm showing you results here for end of century now. Okay? So we're getting in this region now 4.5 degree average warming in Wharf at 10 kilometers resolution, whereas this is somewhat lower actually than the warming that's being predicted from the global model, which is 5.2 degrees. Okay? But again, this number, 4.8 degrees verging on 5, is again almost double the warming, right? That would be expected on the basis of the global model, right? But again, the explanation for the temperature field is very simple. We live on a continent. The heat capacity of continental mass is much lower than oceanic mass, and so a given input of energy will lead to a significant further increase in mean temperature. Looking now at the precipitation field, the results we're getting, again, these are for averages, not for extremes, okay? We're getting 19% average increase in Wharf and 11% increase in CSM, right? Remember, this number is very similar to the result for Ontario and the Great Lakes Basin, properly corrected for the impact of the lakes. And we got an increase in wintertime, and an increase in the north and a decrease in the south. And that the global model is too dry and too hot in summer based on these comparisons. So what about the extremes? So this is another wrinkle in the sort of analysis that we can play in this region, where the number of stations we have to work with is fairly sparse, okay? So over Alberta, we've got a series of red stations, roughly 25 or 30. Here in the coast region, we have many fewer, maybe a dozen or so, right? What we can do is to use a clustering analysis, a formal clustering analysis, by saying we're going to pick all of the stations which have the same climatology, and we're going to put them in the same box and believe that the data sets from each of these stations, right, can be assumed to be pulled from the same statistical distribution. And so to get stability in the predictions of extremes, what we can do is create a long time series by concatenating the time series coming from each station that belongs to a common cluster. Okay? And we'll do the same thing for India. And that proves to be a very important mechanism for doing this kind of analysis when the station density is modest. So this time through, we're not going to do peak over threshold as a means of getting at the fattening of the probability distribution in the tail by using peak over threshold. Here, we're going to use a generalized extreme value distribution method, right, where we fit the data to a GeV distribution. This is getting into statistical minutiae, right? But you'll see that the analysis procedure basically delivers, again, a very similar result. So this slide turns out to be a little bit choppy, but the original fit to the data for the GeV distribution, original fits are shown in blue. Once we bias correct them in the fit to the modern data, we can get the bias corrected fits to very precisely overlap those from the data, right? So again, this issue of bias correction is very important in this analysis. And when we go forward, the net result, basically, by looking at the return time for a precipitation event of a given intensity, right? I'm showing you this here in a slightly different format, but it's basically plotting intensity of precipitation as a function of return time. And basically what you can see is that whereas black is modern for both seasons, right? Red is 2100. Okay? So what you can see is that a given return time, right, decreases markedly in every quantile going forward to the end of the century and for mid-century. So exactly the same thing is happening here on the West Coast in terms of extremes as happened in Ontario. So just to summarize the analyses for Western Canada, there's a significant increase in winter precipitation. In Ontario, the significant increase was summer. Okay? Here on the West Coast, the significant increase is in winter, and the increase is about by 30% by end century. There's a small increase in summer, but more increase in evaporation, which limits the impact, if you like, of the precipitation. But what I want to really draw your attention to is this result, the result in this figure in the top right. The end century soil moisture changes in late summer are huge, okay, right? So we're predicting very significant drying of the entire region of British Columbia west of the Rocky Mountains by the end of the century. And you should understand that drying implies a huge impact on the fire season, potentially. The first of these extreme events that I drew your attention to that BC experienced earlier this year. Now I want to move to the Indian subcontinent. And of course, for precipitation, this is the main event because the Indian continent experiences the summer monsoon circulation. So we're moving now in the same global model as previously. We're rotating the structure, right? Until finally we'll focus on the Indian subcontinent, where we'll do the same kind of analysis by imposing an outer domain and imposing an inner domain, collect data from the inner domain, and then do the detailed extreme events analysis. So we've passed over the Red Sea, and here we're just about, and you can see the precipitation intensity. This is actually through the summer months where the monsoon circulation is occurring, right? And you can see a great intensity of precipitation over that region that's captured even by the global model, right? So the question is, Indian monsoon circulation, precipitation is already the most extreme basically on Earth. Will it be stable going forward, right? Will global warming be such a modest impact on the system that the monsoon circulation cannot expect it to become more severe going forward, or will the contrary be the case? So here are analyses. This is now based on data. This is not model-produced results. This is the intensity of precipitation over the Indian subcontinent, right, averaged by decade, right? Solid line is a decade average. The thin lines are by year, okay? So you can see the huge fluctuations that are involved in yearly variations, right? This is for 86 to 95. This is for 96 to 2005. This is from 2006 to 2016, okay? And here I'm comparing the decadal averages, right, shown dark in the first three of these plates. And you can see that in this representation, it looks as though there's no reason to believe that any increase in severity of the Indian monsoon has occurred, okay? But what about going forward, okay? So again, here is the distribution of the domains. This is the global model in grayscale outside. Here is the outer model of the inner domains, and here is the innermost model focused right on India, okay, on the subcontinent. And I'm showing you this outer domain picture because where we're actually headed is an analysis of the global warming impacts on the Tibetan Plateau in the Himalayas, because you'll understand that basically all of the rivers, right, of southern Eurasia, southeastern Eurasia, are basically fed from the Tibetan Plateau. So the issue of water resources availability, right, in all of the major rivers, the Yellow River, the Yangtze River, right, all of these major rivers are significantly fed by melting off the plateau. So in the end, we're going to be heading to a detailed analysis, not this afternoon, okay, but of action basically on the plateau itself. But here's the data set that we have from India, on the basis of which the last picture was shown. And the station clusters in this case are color-coded. The ones which have, all of the stations which have the same annual cycle, right, of temperature and precipitation, are believed to be drawn from the same statistical distribution. So to stabilize the analysis, what we can do is make a single time series for each cluster to get us enough data in order to serve as a basis for what is expected to happen in that cluster going forward. And here what I'm showing you on the left is basically the impact on the annual cycle in the three main clusters. Cluster 1, if I could go back one step, cluster 1 contains the majority of the stations, which are shown in blue. Okay? It's the data for this region which we can expect to be most stable. The second cluster consists of sites along the east coast, and the third cluster turns out to correspond to a few sites along the west coast, right? Which, because the number of stations is so small, we can't expect really to get significantly stable results from. So if you just focus first on cluster 1, which is the cluster within which we have most of the stations, what you will notice is black is modern. As we go forward, blue to green to red, we're going first to mid-century and then to end century. Okay? And you can see in terms of the mean that at the peak of each of these annual cycles, the peak in the annual cycle is getting stronger and stronger, right? So these analyses very strongly suggest, right, that the monsoon circulation going forward only modestly by mid-century, but by end century in a truly apparent fashion, is going to become significantly more intense than it is under modern conditions. So I want to summarize now the results from both the mean state and the extreme value analysis. So we've got a methodology now which has been developed that serves as a basis for assessing the impact of global warming on weather and climate extremes. It's a very data-intensive analysis, right? This is a big data problem in the modern parlance. It uses enormous amounts of computer resources to make it possible, but it does deliver very stable results which are in accord with expectations. Okay? When applied to regions of both eastern and western Canada, the analysis suggests that extremes of precipitation will increase, and the repeat time between events of a given severity will decrease by mid-century by more than a factor of 2, whether it's eastern Canada, whether it's western Canada, or whether it's India. Okay? The increments in the extremes and the decreased compression of return times are basically the same. But at the bottom now, I want to make the point, which is very important, because the results for each of these regions in terms of the amount of warming on the continent involved, right? The increase in mean precipitation and the increase in extremes are basically the same, okay? So how could that be, right? Well, the answer to that is as simple as was the answer concerning the origins of northern hemisphere polar warming under greenhouse gas increase, okay? It's a simple thermodynamic argument that's based upon a very well-known result from classical thermodynamics, which is called the Clausius-Clapeyron relation, right? The Clausius-Clapeyron relation, a very simple relationship for first-order phase transitions, basically insists that a mere increase in temperature, right, will be accompanied, right, by an increase in the water vapor holding capacity of the atmosphere, right? Okay? So, warm the atmosphere, it will hold more water vapor. More water vapor, of course, is always available from the oceans, okay? And the net result is in the bottom couple of lines at the bottom of this slide. We predict exactly from the Clausius-Clapeyron relationship, right, that an increase of 7% in precipitation should occur for every 1 degree increase in surface temperature. And that's under the assumption that of what we call the temperature lapse rate in the atmosphere remains effectively constant under warming, right? And this is exactly what we found from all 3 of these regions, okay? We know how much warming is predicted at the surface, right? We can therefore predict on the basis of the Clausius-Clapeyron relation by how much precipitation should increase. And we hit that number essentially bang on, okay? So this is explicable in as simple terms as was the explanation, basically, of northern hemisphere polar warming under increased greenhouse gas concentration. Simple thermodynamics. Thank you very much.
Thank you so much for that fascinating presentation. We have time for some questions. If you don't mind repeating the questions after they're said, just so everybody can follow. So.
Regarding the western situation there, in the past it seems that people were worried that Alberta would turn into Dust Bowl because the glaciers would melt too fast in the mountains and the water feed to the west would dry up. But what you're saying is that that won't be the case. You'll have a lot of water staying over the winter in the mountains, and instead you'll have problems in BC in the fall.
Mm-hmm.
Drying out.
No, this is actually a really important question. I didn't speak directly to this, but of course, the Athabasca Basin is to the east of the Continental Divide, and it's in the Athabasca River Basin that the tar sands exist. Okay? So there was clearly, and still is, a huge interest in water resource availability in the Athabasca River. Right? And we've written papers on this, and our result is that it looks as though the impact of warming and water availability in the Athabasca River Basin is going to be reasonably benign. That doesn't mean that the tar sands themselves are benign, but it means that there seems not to be an issue of water resource availability.
Your domains looked mostly rectangular, although the outer domains around India seemed to be curved in a way that didn't match the lines of latitude. sense to make smaller domains that were selecting the actual important local phenomena and a coarser grain for the parts that aren't?
Typically, the boundaries are taken to be surfaces of constant longitude and latitude, which in the projections I'm showing you can look weird, okay, right? But as we come down in area and hopefully focus more strongly on a given region by doing that, we lose stability, right? Unless we embed a third domain, let's say at 3 kilometers resolution. The rule of thumb being in this business that when you project the global model onto a first domain, you can come down or go up in resolution, if I can put it that way, by no more than a factor of 3. And there's been a lot of work determining how much stability you would lose if you were to increase the resolution by more than about a factor of 3 in one step. So that's why we do 100 kilometers to 30 kilometers and then 30 kilometers to 10 kilometers. If you want to get data on, let's say, a 3 kilometer resolution or higher resolution grid, you need to put in an additional eye of the telescope.
And how, I assume because of boundary effects, you don't want the embedded domains near the edge of the domain they're embedded in. Is that right?
Well, in general, yes. Okay? But in the India case, you will may have noticed that the domain over India itself, the western edge of that domain, wasn't very far to the east of the boundary of the outer domain, right? So we had to do a series of analysis to convince ourselves that there was no boundary-boundary interactions. And we've done that, and turns out that that wasn't a problem.
We'll take 2 more questions. What about the woman in the back?
Mm-hmm. Yes.
But what are actually the actions that as a human we can take based on whatever predictions are doing? It is not clear. I understand that it's not clear about this global change, climate change, human impact.
It's very clear that by the end of this century, without changing the course that we're currently following, that there is going to be a very severe price to pay. So we need to implement a policy that will allow our energy system, right, to move away from one which is carbon-based, right? We need to control global emissions. And we're hoping that our current Prime Minister will stick to his guns, right, on the carbon tax issue, right, to help push the country in the direction which will save us from, hopefully, the worst of what will otherwise be in store for us.
Thanks. One last question for now.
I may have missed it, but does your modeling assume any limit on the CO2 concentration? In other words, in terms of emission control worldwide. And secondly, do you feel the scientific community could do anything more in Canada to get the politicians to address the issue? For example, in France, diesel oil today costs 50% more than in Canada. The per capita emissions in Canada right now, in France, are 1/3 of what they are per capita in Canada. And yet we have an electorate who put in know-nothings like Mr. Ford because of 4 cents a litre in gasoline. So,
if you have followed international news in the past 2 weeks, you will understand that the French Prime Minister Macron has been under severe attack because he has increased the price of gasoline at the pumps, right? And unfortunately, he has decided to do this in a non-revenue neutral fashion. This was a very silly mistake, right? Which British Columbia at least didn't make, but of course, British Columbia has stayed fixed at a very low gasoline tax. But this is the politics that we're facing in trying to get the system to do the right thing. So in France, as we have, in the countryside of France, as we have here in Ontario, outside of the city of Toronto, where many, many people are commuting to work by cars, when you increase the price of gasoline, you get a huge negative feedback. For this to be done and accepted, right, it has to be done in a revenue-neutral fashion. And this is unfortunately not what the French government has chosen to do, and so it's bringing all sorts of anger out of the population.
And on the first part of my question, does your modeling assume any limit on CO2 in the atmosphere?
No.
Okay, so.
No. I mean, it used to be thought, for example, that all of the absorption lines, would be saturated at some point, and once you got to a certain level of CO2, adding more would do nothing, and this is just not the case.
Okay, please join us for coffee after the talk, where you can speak more to Dick Peltier and ask him your questions in person. And thank you on behalf of RCI. We have a thank you gift for